American military planners looked at this ocean of Soviet steel with growing concern. Their own tanks, like the M60 Patton, were good, they were reliable. But were they good enough to stop the red tide? The fear was that they were becoming outmatched, not just in numbers but in future potential. A new kind of tank was needed, one that could dominate the battlefield of tomorrow. This new tank needed to be a leap forward in every way. It required revolutionary armor. It needed a powerful gun, but most of all, it needed speed and agility. The ability to move quickly, to get into position first, to outmaneuver the enemy. This was seen as the key to survival and victory. A tank that could shoot and move, and do both better than anyone else, would be a game changer. The American Army began a quest for this super tank, a project that would eventually become the legendary M1 Abrams. But building a super tank is easier said than done. Every single component presented a monumental challenge. The armor had to be stronger but not excessively heavy. The gun had to be more lethal but still fit within a turret. And the engine, the very heart of the machine, had to provide unprecedented power. The engine was the linchpin. It had to propel over 60 tons of steel across rough terrain at incredible speeds. It had to be reliable in the heat of battle, from the frozen German winters to the scorching desert sands. The search for this perfect engine would lead American engineers down a radical and controversial path. For decades, the undisputed champion of tank propulsion was the diesel engine. It was the workhorse, the reliable heart of armored vehicles around the world. Diesel engines were powerful, fuel-efficient, and relatively easy to maintain. They had proven themselves in the mud of the Eastern Front and the deserts of North Africa during World War II. For the designers of the M60 Patton, sticking with a diesel engine was a logical choice. It was the technology they knew and trusted. It made sense. But as the demands for the next generation of tank grew, the limits of diesel power started to show. The problem was a simple one of physics. To make a tank faster and more agile, you needed more horsepower. To get more horsepower from a traditional diesel engine, you had to make it bigger. A bigger engine meant more cylinders, more weight, and more space. This created a vicious cycle. A heavier engine required a stronger, heavier chassis to support it. The extra weight then required even more power to move it, which in turn meant a bigger engine. Designers were hitting a wall. The diesel engines were becoming monstrously large and complex, eating up valuable space inside the tank that could be used for ammunition or crew comfort. Furthermore, diesel engines had a distinct battlefield signature. They produced thick black smoke when the driver put his foot down, creating a tell that could give away a tank position to the enemy. They were also incredibly noisy, with a low, rumbling growl that could be heard from miles away. In an age of increasingly sophisticated sensors and targeting systems, stealth was becoming more important. What if you could take the engine from a jet and put it in a tank? The idea seemed like something out of science fiction. Gas turbine engines were the power behind the fastest aircraft in the world. They were known for producing enormous amounts of power from a remarkably small and lightweight unit. A turbine works by sucking in air, compressing it, mixing it with fuel, and igniting it. Cutaway diagram showing compressor, combustor, and turbine sections. This creates a blast of hot gas that spins a turbine which can then be used to turn a drive shaft. It was elegant, powerful, and completely different from the chugging pistons of a diesel engine. The appeal of a turbine for a tank was immense. First, there was the power-to-weight ratio. A gas turbine could produce the same horsepower as a diesel engine that was twice its size and weight. This was the holy grail for tank designers. A smaller engine meant more room inside the tank. It meant the overall vehicle could be lighter, or the weight saved could be used for thicker armor or more ammunition. It promised to shatter the design constraints that had plagued engineers for years. A turbine-powered tank could, in theory, be faster and better protected than any diesel-powered rival. There were other advantages, too. Turbine engines are mechanically much simpler than piston engines. They have far fewer moving parts. A typical diesel engine has hundreds of components whirring and reciprocating, creating friction and wear. A turbine has a single main rotating shaft. This simplicity suggested it could be more reliable and easier to maintain in the long run. Even more tantalizing was its multi-fuel capability. A turbine could run on almost anything that burns, from diesel, gasoline, kerosene, high-proof alcohol. This logistical flexibility was a commander dream, but the idea was not without its critics. The challenges were just as significant as the potential rewards. Gas turbines were notoriously thirsty, consuming fuel at a prodigious rate, especially at idle. Could a tank carry enough fuel to have a decent operational range? They also produced an enormous amount of heat, with an exhaust so hot it could incinerate anything behind it. This created a huge thermal signature, making the tank a glowing target for heat-seeking missiles. And while mechanically simple, the technology was exotic and expensive. Could a jet engine really be tough enough to survive the grit, mud, and abuse of a battlefield? The dream of a turbine-powered tank did not appear out of thin air. It was championed by a small group of determined engineers, primarily at the Lycoming Turbine Engine Division, later acquired by Chrysler. These were the true pioneers who believed when most of the defense establishment was skeptical. They saw the future, a high-pitched whine, not a low-frequency rumble. Their work began long before the M1 Abrams was even a concept, experimenting with turbines in the 1950s and the 60s, driven by a belief that they were onto something big. At the heart of this effort was the development of a specific engine, the one that would ultimately power the Abrams. It was designated the AGT 1500, Automotive Gas Turbine, 1500 horsepower. This was not just a modified aircraft engine. It was designed from the ground up for the unique and brutal demands of a ground combat vehicle. The engineers at Chrysler faced a mountain of technical hurdles. They had to figure out how to make the engine survive the dust and debris that a tank kicks up. An aircraft engine operates in the clean air of the sky. A tank engine lives in a perpetual dust storm. The solution was a complex and highly effective air filtration system. It was a multi-stage marvel of engineering, designed to capture sand and dirt before it could enter the engine core and shred the delicate turbine blades. Another key innovation was the heat exchanger or recuperator. This device was crucial to tackling the turbine's terrible fuel economy. It captured waste heat from the exhaust and used it to preheat the incoming air before combustion. This meant the engine used less fuel to get the air to the right temperature, dramatically improving its efficiency, especially at lower power settings. It was a critical breakthrough. These engineers were not just lab-bound academics. They were hands-on problem solvers. After years of development, the moment of truth arrived. The AGT 1500 turbine engine was ready to be tested in an actual tank. The Army had initiated the XM-1 program to find its next main battle tank. Two contenders emerged, one designed from General Motors, and one from Chrysler. The GM prototype used a conventional, though advanced, diesel engine. The Chrysler prototype was built around the revolutionary AGT 1500 turbine. This set the stage for a head-to-head competition on the proving grounds. The first time the Chrysler prototype, with its turbine heart, roared to life. It was unlike anything anyone had ever heard from a tank before. Instead of the familiar diesel clatter and rumble, there was a deep whoosh of air being sucked in, followed by a rising, high-pitched whine, like a jet preparing for takeoff. It was a startling, futuristic sound. When the driver engaged the transmission, the tank didn't accelerate with an unnerving smoothness. The power delivery was instantaneous. The tank seemed to glide across the terrain with agility that left observers stunned. This incredible acceleration became one of the turbine's signature traits. It was quickly nicknamed "Whispering Death" by the soldiers testing it. It was quiet at a distance, its high-frequency sound dissipating more easily than the low rumble of a diesel. This gave it a crucial element of surprise. Test crews reported getting much closer to mock enemy positions before being detected. On the battlefield, that could mean the difference between firing first or being destroyed. The turbine was not just powerful, it was stealthy in a way no one had anticipated. But the early tests were not all smooth sailing. The new technology had its teething problems. The complex air filters sometimes clogged in extremely dusty conditions, choking the engine of power. The early recuperators, vital for fuel efficiency, sometimes developed cracks from intense heat and vibration, leading to engine failures. Each setback was a blow to the program and ammunition for critics who favored the safer diesel option. Chrysler engineers scrambled to diagnose the problem, redesign the part, and get the prototypes running again. It was a high-stakes race against time and doubt. In November 1976, the Army made its stunning announcement: the Chrysler prototype with the AGT 1500 gas turbine engine had been selected. The revolution had